So the beginning of this handout basically starts with exactly what we talked about a little bit a couple classes ago. The idea of a rational function means we're going to be looking at functions that look like this. Functions that look like big scary fractions. The numerator and the denominators of these scary fraction functions are polynomials. So yeah, here's the irony of you not knowing how to do polynomials. The stuff you can't do for polynomials, it's going to mess you up on rationals too. But the flip side of that is, if you focus now on what we're doing with rationals, that might be enough to actually get you back on track for polynomials as well. So two flip sides. If you're still not going to do anything, this is going to continue to suck. If you're going to do stuff, this could actually help you understand the polynomial stuff, because we're going to use all the polynomial skills to do these problems. Our first job with our rational functions is to find the domain. To find the domain, we have to find the zeros of the denominator. And then basically, those numbers are the numbers we're going to not include on our domain. So how are we going to find the domain of a rational function? We're going to figure out where the denominator of the rational function equals 0. X squared minus 4x minus 12 equals 0. Our number one technique for solving that, for coming up with zeros of a quadratic, is factoring. And I've given you a lot of examples as we're working. So here we go. This kind of comes down to the bottom line of, if we're crappy at factoring, a lot of bad things are going to happen. So we got to get this under control. So who can tell me, what do I have to look for to build these factors? Raise your hand if you can tell me. What do you have to look for to build factors? Ronnie, what are we going to look at? We can look for a GCF first. That's a good plan. When I look at this problem and I look at x squared versus 4x versus 12, do you see something that's a GCF? Say that again? Well, the 4 will work for the 4x and the 12, but not the x squared. So I can't use 4. Okay, so before we get to that, back to GCF. I can't take an x out of all of them because they all don't have an x in them. I can't take a 4 out of all of them because they all don't have 4s in them. So I would say no GCF to factor. Okay. No GCF to factor out. Okay. So now we can go to, we're basically going to try to see if we can build 2 binomials as my factors. So what do I have to look for to start building these factors? Ooh. Summer? Yeah, okay, yay, okay, go Summer. Okay, so factors of negative 12. Okay, so make a little, so some of you guys do like a little x. How about I'll use your little x? So negative 12 factors, negative 4. That's a 1. So if you think about it kind of with the other kind of problems, when this is not a 1, it's a little harder because you have to remember to take this times this to get that number. When it's a 1, it's a little easier. All right, so factors of negative 12 add up to negative 4. A 6 and a 2 with the 6 negative. Are we okay? Okay. So then, -6 and +2, x squared, x and x, and there are our factors. If these all had an x in them, we could factor an x out first and then try doing something like this. That's where most of you got stuck. If it was just a quadratic, some of you guys were fine factoring it in most cases. If there was a GCF, that's where we got a little tricked up. So we'll definitely work on that a little bit more. Okay. Now, each factor I set equal to 0 and solve. So x equals 6. Whoops. And x equals -2. Another mistake I saw some people make is when you build your factors, you're like, oh, -6 and 2. So then you use those as the zeros. The -6 and the -2 and the 2 build the factors. So the zeros or the roots or the x-intercepts for when we were doing our polynomials have to be the +6 to make x minus 6 factor equal to 0, -2 to make the x plus 2 factor equal 0. So then, how do I write the domain? I basically start from -infinity up to my first 0 of the denominator. And I'm going to put a curve because I'm not going to include that number. So I'm basically saying, here are the x's that'll work for this function from -infinity up to -2. But -2 is no good. From -2 to 6 is all good. But -2 is no good, 6 is no good. And 6 to infinity. That's kind of a long way to say, what are the x's I can plug into this function? Every x I can think of will work except a -2 and a 6. Because if I put a -2 in the denominator, it's going to make a 0, and that means that the function's undefined. If I put a 6 in the denominator, that means the denominator will equal 0 and the function is undefined. Okay. So, here's what I want you to do for this one. Before we talk about a whole, which will be the next idea, I want you to look at both of these, example 1 and example 2, focus just on the denominator, and find the domain for me. Okay, just the denominator, because that is where we go for the domain. The first one's a little bit easier than the second one. The second one, you gotta do a little factor. The bottom's gonna be for domain. We're gonna ignore it for now. Eventually, we're gonna worry about it. Okay, so yeah, we're gonna ignore the top for now. Look at your denominator. Figure out the numbers that make your denominator go there. Yeah. Not on a domain. Not on this. Not on a rational function domain. We're always looking for the numbers we're going to eliminate. So it's always. How did we get to that? No. Yeah, you can do that. You can do. That's exactly. And then figure out where they're equal to 0. Yeah. So yeah, once you build your factors, then you just take each factor and think about, okay, if this factor equals 0, what would the x have to be? So make your factors and then think about your factors. Yes, sir. So this one's easy because it's just that. So what number will make that equal 0? If x plus 2 equals 0, how would you solve for x? Well, I think you've got 1x, and then you've got plus 2. I think you got to get rid of the adding and subtracting first. Right? So 1x equals -2. So if you divide by 1, so x would equal -2. Good. Okay, so that means this is a number that is the number you're going to skip over in your domain. So when I write my domain out, I'm always going to start with negative infinity. So I'll go negative infinity to -2 in this case. And then, what do you think the rest of it? Start over at -2. And there's nothing else special. So go over to infinity. There you go. Stuff. Okay, so now we got to do the same kind of thing here, but we got to factor. The x-intercepts is tricky because x-intercepts are from the numerator, but things that are not whole. So you got to find the whole first. So 3 is not an x-intercept. Yes, only -2 would be the answer. Yeah, I know, you remember a lot of that from. Okay. Yeah, so this factoring in problem 2, if you don't remember that factoring, that's that difference of squares factoring. We actually love that kind of factoring because it's quick and dirty. X squared minus 4, since they're both perfect squares, your factors are going to be x plus 2, x minus 2. The square root of x squared is x. The square root of 4 is 2. And the plus and the minus is what makes it, when you FOIL it back together, gets you the thing where they add out to 0. Okay? So x plus 2 equals 0, x equals -2. So I saw a lot of you had this. Negative infinity to -2, -2 to infinity. The domain is going to break into as many pieces as zeros from your denominator. So when I do example 2, and I take x plus 2 and x minus 2 as my factors, and one of them gives me -2 for x, and one of them gives me +2 for x. Then when I create my domain, I'm going to go, whoops, okay, negative infinity to the -2, and then start with the -2 to go to the 2, and then from 2 to infinity. The domain also kind of gives you an idea of how many pieces of graph you're going to have. Rational functions can be, a lot of the times, are in pieces. They're not just all one big connected chunk. So the domain being in 2 pieces here tells me this graph is going to be in 2 sections. This domain being in 3 pieces tells me there's going to be 3 sections. It's a little tricky because sometimes the sections, the thing that divides them is just one little hole. But basically we're going to have 3, I'm going to be able to look at 3 pieces of graph, 2 spots where the graph kind of breaks apart. Okay. So this is the domain question, is what the question was for you to do on this. It was just 5 questions where I asked you to take the function, figure out the domain. by essentially factoring the denominator and identifying the zeros of the denominator. So if you didn't do this assignment, like I said, please do it. Okay. It's not self-checking. You're going to have to type your own answers in. So you won't know if what you're typing in is right or not. I'm going to go through and look at them, and I'm not going to grade it in terms of, I'm going to let you know how many you got right, but I'm not going to record a grade based on how many you got right. I'm going to record a grade based on you did it. Okay? So try it. Do it. It's practice. It's practice for factoring and writing domains. Okay, now, we're going to do next, we're going to identify a graph having a hole. And in order to have a graph that has a hole in it, to know that we're going to have a hole in the graph, we're going to see, after factoring the numerator, a common factor in the numerator and the denominator. Okay, so I'm going to go ahead and get myself a clean sheet because I am very messy in writing everything all over the place. And this way, later on, if your notes are a little messy, you'll have a nicer version that you can print out or look at. So let's take a look at this first problem. What was that, a +8, right? Okay. So number one, we find the domain, and when we're in the process of finding the domain, sometimes that's going to require factoring the denominator. Rational functions have a lot of steps. The best way to remember a lot of steps is to kind of do them in the same order all the time. And so that's what I'm going to do, is I'm going to teach you to do these in a certain order. If you want to do them in a different order, it's okay. There's nothing wrong with it. This is not the only way to do the only order, but it's the order that makes sense to me. And it's usually the order that I find has been helpful. So domain, denominator, start there. Factor out your denominator, get your domain. Check. Number two, we're going to go looking for holes. And part of the search for holes is going to be you factoring the numerator. Okay. And looking to see if the numerator and denominator have a matching factor. We're going to do a lot of practice problems where we are going to have a matching factor, but not every one of rational functions out there has that. But if I want you to practice that, I got to kind of give you problems that have that in there. So if we're practicing looking for holes, that probably means that there's holes in there. All right. So we didn't really have to factor the denominator to get the domain of this problem, but we are going to have to factor the numerator in our procedure of looking for a hole. Okay. So I will leave the denominator just sitting there. Nothing, didn't have to factor anything on that one because it was just a linear function. And if I factor factors of 8 that add up to 6, 4 and 2, when this is just a 1, they can go directly in the parentheses. When it's not a 1, you've got to split up the middle. If you want to do the splitting the middle, if you're doing that and you're still getting these, that's fine. That's a little bit of a longer way to factor this, but it doesn't mean that it's wrong to do that. You can absolutely use that same strategy that we used when the the number in the front is like a 2 or a 3, and do that same thing when the number's a 1. Yes?
So if the x has, if the exponent of the x is 3, can you still just put it in, or do you have to
If the exponent on the x is a 3, you would have to do a GCF first and get it to a quadratic. See, this is going from here to here is specific for a quadratic, a degree 2, or an exponent of 2 with a power 1. Okay, that's a good question. Okay. Is there a hole in this function? Yes or no? Yes. How do you know there's a hole in this function? You got a matching factor, right? This guy and this guy. Right? And watch this. So that matching factor of x plus 2, you set that equal to 0 and solve. That means I know there's going to be a hole in this function at x equals negative 2. Okay, let me show you something here. And I'll put that back up. Let me grab this for a second. Come here, Mr. Schoology page. Come back over here for me while you're looking at that. Boop, boop, boop. Desmos. And yeah. Oops, not that. Get out of the way, Mr. Typey. Okay, there we go. Sorry. I'm making you a picture now. Squared plus 6ax plus 8. And we're going to divide that by x plus 2. Okay. Here's what's tricky about this. Rational functions can look kind of just like normal friendly functions. Like this guy, when I type him in Desmos and graph him, you're like, well, that's like a line. Where is that hole that you were talking about? Desmos doesn't show them until, if you click though and drag, when you get to, oh, it's hard to get there, but you can see when I get to x equals negative 2, it tells me the function's undefined. And it actually, you can look, even does it with the point. Every else place, the point is solid. But when I get right there, it is like a little open circle, if you can see around my cursor. That's how Desmos is going to show us that there's a hole. So if you wanted to check, because this is not how we're going to do our problems. We're not going to type it all in Desmos and then just tell everybody what Desmos says. We're going to predict what's going to happen. But typing it in Desmos is definitely a way to sort of check and say, well, look, there's my hole, just like I predicted at x equals negative 2. That's why the domain is the x's on this graph are all of the x's except negative 2. Because at negative 2, the function goes undefined. Now on the graph, it's easy to see where the y value of the hole, what y value matches up with the hole. If I go to the graph and I'm like, oh look, it looks like when x is negative 2 and it makes the hole, it also lines up with about a y of 2. We want to be able to figure that part out without the graph, and that's what we're going to do next. All right, this is probably everybody's least favorite part. However, this is actually the part you're going to use later if you do end up taking calculus, when we do limit questions and we have a hole. So we have a hole at x equals negative 2. you're now going to make me a new function with no hole. So look at up here, I have the whole of x plus 2 and the whole of x plus 2. Bam, bam. And so my new function, oh, I'm not writing in highlighter, even though that would be fun. Wouldn't be very easy to read. F of x equals x plus 4. And when I took the x plus 2 away, it's a 1. The new function is going to be a friendlier version of the original function. The new function is our friend. The function without the hole basically tells us exactly what this function is going to look like. It looks just like the line y equals x plus 4. And that's what Desmos is showing me. If I do the line y equals x plus 4, that graphed right on top of my red function. This is the scary function. This is the x plus 4 function. They're secretly exactly the same, except when I'm on x plus 4 and I go to x equals 2, it's not a hole anymore. This guy look exactly the same everywhere except the spot where the hole is. The hole gets filled in. That's a trick we're going to use over and over again. We're going to make a new function. We're going to take away the hole. And then this new function we're going to use for everything else we're going to do. Now look how happy and nice that new function is. In this new function, f of negative 2, if I plug negative 2 into the function, I would get 2. So that tells me 2 pieces of information about the hole that I need. That I found that the x of the hole was negative 2, and the y of the hole is 2. So, yes, sir. Yep, here, come get a pass. We gotta follow our new pass rules. There you go. So, here we go. Back to the top. Factor the denominator, that's gonna get us our domain, and we're gonna use that to help us do holes. So basically, we're gonna factor the denominator and factor the numerator. If you just do the denominator first and do the domain, and then jump to the numerator, do the numerator, look for the hole, find the x of the hole, make a new function, use the new function to find the y. All right. So I want everybody to try the next 2 problems. Meaning, I want you to take example 2 and find the hole. And then I want you to take this guy and write the domain and find a hole. I will rewrite that on another page so we have some space. So we're taking x squared x plus 10 over minus 4. Find the hole. And then 2x minus 6 over squared minus 10x 21. Write the domain. Find the hole. And when I say I want you to find the hole, that means you're going through the whole thing where you're going to figure out the x value of the hole, you're going to make new function, and then then you're going to find y value of whole. All right, here I come. Here's my super tight shirt. Like a sausage. That is okay. It's tradition. We wear a jersey. I'm proud. Even though I'm chubby. Proud and chubby. How we doing? And I know some of you are like, I remember this, and you're working ahead. That's totally fine. Everybody's going to do this at a different pace. That's kind of why I built a lot of stuff into this packet. No, you're not. How are you terrible at it? Okay, so you factor the denominator, right? Just denominator builds domain. D for denominator, D for domain. So zeros of the denominator break apart the domain. So on my denominator breaks out to a 7 and a 3 that are my zeros.
And then
Right?
y.
So
Yeah, that's
well, no, no, no.
but you have to
These numbers.
So
These numbers.
you.
Yep. And then, boy, yeah, well, no,
Okay,
because
so
wherever
these
you
are the
end, you gotta start.
Right, this
Yeah.
is the whole.
There you go.
And then you just,
And,
you got that.
Yep, there you go.
And then basically the rest of you fill in the.
Okay. Okay, yeah.
After you do that, you.
Okay, so we're gonna,
You bring it back and.
Okay. we're gonna have to write that using factors as well. Now that's, there's not a lot you can do to that, but this does have a GCF. I can factor a 2 out of both of those. And so if I rewrite the top of this as 2 times x minus 3, and then I look at the denominator, no, so if you take, if you think about it, you have this, I can do that, right? And that would be that. So the 2 I divided by goes out there. And then how you did that so nicely goes down there. And here comes your hole. Well, you're gonna, the 3 that you, it's gonna come from these guys, is gonna be at x of the whole. We're gonna take, and then we're gonna throw those guys away, have a new function, and then plug the 3 into that to get the y. 3, 4, 5, we go for x. Is 3 and okay, so the problem here, factoring is not throwing away. So when you factor a 2 out of this, you're still gonna have a 2 in there. You're gonna have 2, not x equals 2, no, you're gonna have a factor of 2. Because 2x minus 6, a multiplication problem that equals 2x minus 6 would be a 2 times x minus 3. And you'll have a 2 up there. So when you take out the x minus 3, you'll still have a 2 up in the numerator.
Yeah, not anymore.
How are you doing? I like that. Okay, so show me how you're gonna do that. Yeah. So factors of 21. So 21 at the top, negative 10 at the bottom. Yes. Yeah, like not available is good, or not.
Plus 2 would be negative.
You always have a y-intercept though. You substitute a y-intercept, substitute 0
Plus
into x,
x minus 2.
and simplify the whole function.
It's x minus 5.
Yeah, yeah, because you don't have anything to clean up. Okay, so you see the matching guy. So the matching guy, the x from the matching guy is the x of the whole. Okay? So where we make our new function. Take out, we rewrite the function, so these are this, and then you set this to it. I'm gonna go through that again. Okay, so let's, yeah, here. First of all, I like how everybody's kind of talking to me, and I know some of you are kind of going faster than others, and that's fine. Let me take a second here and. Yep. Yes, have to leave it. So you're going to use that when you find the y of the whole. Your whole is definitely 2, and then you did. You did that, and you wrote that, but then say, why did you write? Because you went cuckoo at the very end. Okay. All right. I guess our homework's going to have to be make a TikTok where you show how to find the whole. All right? First you do this, then you do this. It's kind of the same thing, though. You have to memorize like kind of a routine. So here we go. I'm finding the whole. And no, I'm not. I'm lying. I'm not finding the whole that way because that doesn't factor. So if I'm finding the whole, oh my goodness, I was recording the whole.